Okay, so today we want to move to a new topic, which is default reasoning. Now, there is a whole variety of approaches which fall under what we call reasoning under uncertainty. And default reasoning is what we are interested in. It is a kind of a one way of handling that. So, you can say this is like making inferences with incomplete knowledge or incomplete information. So, the basic idea here is that you do not know everything, you do not know all the facts that are true in a given domain, which is of course true in the real world. We do not really know what is happening in many places or what is true in many places. So, given the fact that you are working with incomplete information, what are the kind of inferences you can make is the topic of default reasoning essentially. We also use the term non monotonic reasoning. Which comes from the fact that the set of inferences does not grow monotonically. So, by this we mean that if you know a certain knowledge base and then you can infer a certain set of sentences from a knowledge base. Then if you add some more facts to the knowledge base, it is not necessary that whatever you could entail with the smaller knowledge base will also hold true with the newer knowledge base essentially. So, the set of statements you can infer may decrease or may go up, both ways it could happen essentially. Whereas, in classical logic, if you have a set of statements or knowledge base, then whatever you can infer from it is not affected by adding more statements to the knowledge base. So, classical logic is monotonic in the sense that you add more statements and you can make more inferences, or you can infer more facts. In non monotonic reasoning or non monotonic logics, you add more statements and you may have to actually retract certain inferences that you had made earlier essentially. So, we will see this kind of reasoning today. Now, one of the main problems with using classical logic is that statements are rarely true universally. There are very few statements in fact you can find which are true universally. So, people say that there are only two certainties in life, one is taxes and the other is death. So, let us not talk about taxes, which is so, but we can talk about death for example. And if we talk about death, for example, we have our good old statement, for all x man x implies mortal x. It is a universal statement that if you are a human being, you will die one day essentially. That is one of the very few universal statements you can come across essentially. Very often you want to make statements, statements are often general. So, for example, you might say children like to play. Now, this is a statement which may not necessarily be true for all children. I mean, who knows, there is some child somewhere who does not want to play essentially. Or you may say something like German trains are always on time or are on time. Might be hard to believe, but I know of a case about 15 years ago when there was a train which was 7 minutes late in Germany. So, we cannot, with statements like this, children like to play, German trains are on time, the statement that we will often use, birds fly, and so on and so forth. These are not universal statements, they are general statements, in the sense that we cannot say that the formula is universally true. So, for example, if I take this first example, if I say this for all x, child x implies, let us say plays stands for likes to play x essentially, and then I say I have a large knowledge base of children, and somewhere in this knowledge base I say child, let us say Suresh, and if I say not plays Suresh. So, for some reason let us say Suresh does not like to play. So, I have a counter example essentially for this universal rule. The universal rule says that all children like to play, and then I have a counter example that Suresh is a child and Suresh does not like to play. Now, if you look at these three set of statements, these are unsatisfiable. So, the point is that if you use the universal statement that all p's are q or that kind of a statement, and if you suddenly find there is a p which is not a q, then your knowledge base becomes unsatisfiable or inconsistent, and we have seen that from an unsatisfiable knowledge base or from an inconsistent knowledge base you can derive anything essentially. So, it is kind of pointless to have an unsatisfiable knowledge base, which means of course, to make it satisfiable we have to remove some statement, and assuming that our factual knowledge about Suresh is true, that Suresh is a child and Suresh does not like to play, the only thing that we are left to retract is the statement that all children like to play. So, we would like to build a reasoning system which will not insist on using a universal statement, but will use a general statement essentially like children like to play, which means that most children like to play or things like that essentially. Now, there are many different ways that people have tried to handle this kind of information. So, people may use probabilistic reasoning, they say if x is a child and probability is 0.9 that the child wants to play and things like that. And then there are things like rough sets and things like that, which is that necessarily true and possibly true and that kind of stuff. The approach that we want to take in default reasoning is that build a mechanism for arriving at conclusions in such a manner that if necessary you may have to withdraw conclusions later essentially. So, it is kind of a little bit a continuation of what we studied in the recent past, which is when we talked about extensions of inheritance hierarchies. So, we talked about inheritance hierarchies and we said what can we believe about an individual A, and we found that there could be more than one credulous beliefs about an individual A essentially. So, here also because we do not know enough about the world that we are reasoning in, we may want to draw conclusions, because most of the time those conclusions will be true. So, all these statements, children like to play, German trains are on time, birds fly and so on and so forth, will generally be true. So, if you say Tweety is a bird, it is reasonable to make an inference that Tweety can fly essentially, or if you say that Sita is a child, it is reasonable to assume that Sita likes to play essentially, and we would like to make some inferences, because the whole point of making general statements or universal statements is compactness. We do not want to represent the same thing for every individual. We want to use quantifiers, existential quantifiers or universal quantifiers, and try to talk about the entire domain or entire subsets of the domain and things like that essentially. So, our goal in the next few classes would be to look at different forms of default reasoning. We will start with the simplest one, which is called closed world assumption. So, let us say we have a knowledge base in which we have some set of atomic sentences. Closed world assumption says that it is like negation by failure essentially. It says that if you cannot show a sentence to be true, it must be false, and we are talking about atomic sentences, then it must be false essentially. So, we are assuming that we know everything about the world. If we do not know something, then it must be false. So, let us say we are talking about people liking ice cream essentially. So, if I say Ramesh likes ice cream and Geeta likes ice cream, if I do not make the statement about other individuals in the domain, it means they do not like ice cream essentially. So, that is a closed world assumption that we are talking about. So, what do? We in closed world assumption, we work with a new knowledge base which we call as KB plus, and we define it to be KB, which is the old knowledge base, union the set of all negative statements such that P is atomic and the knowledge base does not entail P. So, either P is not present, or somehow we cannot derive P from the knowledge base. As long as we cannot derive P, it is in some sense consistent to add not P. And this is a general theme of default reasoning, is that if it is consistent to believe something, then go ahead and make that belief, which means that if you make an opposite belief, then you would, or by adding that belief, you are not making the system inconsistent essentially. So, I might say that students like to study essentially. Now, this of course should follow from the definition of the word student, but it may not necessarily always be true. So, which is not necessarily a universal statement. In fact, as a small thinking exercise or armchair exercise, I would sort of urge you to try to find some universally true implications. For all x, p x implies q x, where all can you find statements where this is universally true, which means it can never have an exception, which means you can add it to the knowledge base essentially. So, the general idea in default reasoning is that if it is consistent to believe that a student likes to study, then infer for a student that the student likes to study. So, it looks like a slightly roundabout statement, but essentially we are saying that if let us say Ramesh is a student is given to us, and then we have this very complicated statement which says that if it is consistent to believe that students like to study, then make the inference that students like to study. One way of thinking about this is that if Ramesh is a student, and if you cannot show that Ramesh does not like to study, then make the inference that Ramesh likes to study. So, in between there is this clause which says if you cannot show that he does not like to study. So, which is very similar to this, but there are variations that we will see. Closed wall assumption is very simple. It simply says that for every atomic sentence, if you cannot, if it is not entailed by the knowledge base, then you can add its negation to the this thing. And we are talking at the moment of propositional logic, and in a moment we will move to first order logic as well. And then we say that a knowledge base entails under the closed world some formula alpha if the knowledge base plus entails alpha. So, just read this formula carefully. On the right hand side is that we have the augmented knowledge base in which we have added these negative statements, and from that if we can derive alpha using the usual notion of entailment, we are now defining a new notion of entailment which is underscored with the letter C, which stands for closed world assumption, that we say that alpha can be derived from the knowledge base if alpha can be derived from the augmented knowledge base using the normal notion of entailment essentially. So, this is the basic idea behind closed world assumption, and we have these rules which we have these rules, the semantics that you can sort of imply as to how to break up larger formulas into smaller formulas. So, if you have a formula of the kind alpha and beta, then if you can individually show alpha and beta to be entailed, then you are through and that kind of stuff essentially. Yeah.
It's an F, it's not an F and only F.
Well, we are not really interested in the other way around. I think we are simply saying that if you if from the augmented knowledge base you can derive alpha, then you have derived closed world assumption. It could be an if and only if, but that is not really important. Okay, now there are two kinds of properties we would like to talk about. One is completeness, and we are talking about the closed world reasoning or default reasoning. Is that can we answer? So, for every atomic sentence, we should be able to answer yes. So, let us say the sentence is P. So, either for P or for not P, and the relation between not will be eventually the same as the usual notion of negation, which means that if you can entail P, then you cannot entail not P. If you can entail not P, you can entail P and so on. So, that is the notion of completeness, which says that for every atomic statement I should be able to say whether under the closed world assumption whether the statement is true or false essentially. And the other thing is consistency. So, should not entail alpha and not alpha, the usual notion of consistency, that you should not be able to derive both a formula and its negation essentially. So, let us look at an example. And the example is from this book Brackman and Levesque. So, we have a predicate C x y which says that city x is connected to city y. So, So, let us say there are 5 cities in my knowledge base. Let us just for want of better names just use the letters A, B, C, D, E, and my knowledge base is as follows: connected A, B, connected B, C, connected A, D, connected D, E, some random statements essentially. Now, if I use this closed world assumption that I had just stated, that I extend the knowledge base by adding, we have only one simple predicate in this example. We are just trying to illustrate what is happening. Given this knowledge base, is closed world reasoning complete? That is the question I am asking you. So, which means can I answer this question? The knowledge base entails under closed world reasoning the fact that A is connected to E. Can we answer this question? Yes or no? I am not asking you, I mean looking at this knowledge base, what does this mean? This means that we are translating it to a query which says, does the knowledge base plus entail C, A, E, or does the knowledge base plus. So, we are assuming at this moment that it is consistent, not C, A, E. So, remember that the notion of consistency says that you can answer only one of them with yes essentially and one of them with no. What is knowledge base plus here? It says that for everything that I cannot derive, for every other pair of cities that I cannot talk about, I should add the fact that negative. So, in fact, the knowledge base plus will be this K B that I have union all other things. For example, not A. So, I have A connected to B and to D. So, I can say not connected A C essentially, and so on, and eventually I will also have not connected A E. So, I have this fact here in the extended knowledge base. So, in this extended knowledge base I have this fact here. So, I can say this is true and therefore, this is false essentially. Right. So, you can see that the system is both complete. You choose any 2 cities and I will be able to tell you whether they are connected or not essentially. This is relying on the fact on the closed world assumption, which says that if they are connected I would have stated them in the this thing. Here we are, I have not used implication and so on, but you can sort of carry forward this idea. Here entailment is simply presence in the knowledge base or not present in the knowledge base in the extended knowledge base essentially. But you can see that the system is complete and the system is also consistent essentially. Are there any problems? there is a problem which comes with disjunction. Disjunction is almost always a problem in computing. So, let me take a simple knowledge base. Just one statement P or Q, just one statement, let P and Q be some propositional statements, and I have a simple knowledge base P and Q. What will be my knowledge base plus? It will be this statement P or Q, and because I cannot show P to be true, I will add not P, and because I cannot show Q to be true, I will add not Q, this thing. You see this by the simple definition that I can, for every atomic statement there are only two atomic statements P and Q here. If you cannot show them to be true, then you must add its negation. So, in this case I only know that P or Q is true, I do not know whether P is true or Q is true. So, since I cannot show P to be true, I can add not P, and since I also cannot show Q to be true, I can add not Q. But what is the problem with this? This is inconsistent. So, we are not able to handle disjunctions essentially. So, the solution that has been proposed is called generalized closed world assumption, GCWA, and this says that extend the knowledge base, which says that if a atomic sentence is participating in a disjunction, do not indiscriminately add its negation essentially. You can add its negation only if the rest of the disjunction can be shown to be true essentially, which we can write as follows, that we have a different this thing, we will use a star now, is equal to union the set of all those atomic statements which are and if the knowledge base entails P or Q or R or S, as an example I am choosing, then the knowledge base entails Q or R or S. So, to a participant in a disjunct P or Q or R or S I have chosen, you can add a negation of P only if the rest of the disjunct is entailed by the knowledge base. So, this is kind of more conservative, it will not randomly add all negation statements here essentially. So, with this example that we are looking at above, you can see that K B star in the example here is equal to K B in fact. We do not add anything to that essentially. So, it is more conservative essentially. So, this is consistent but not complete. So, under the generalized closed world assumption, you will only give create knowledge bases, extended knowledge bases which are consistent, but you will not be able to answer questions about individual atomic predicates, which means that there are certain sentences that you will, which are composed using those atomic sentences, you will not be able to answer. So, in this particular example, you cannot say whether P is true or whether P is false, or whether Q is true or whether Q is false. So, the closed wall assumption was kind of eager to say everything it does not know is false. The generalized closed wall assumption is a little bit careful, especially when it comes to treating disjunctions. For knowledge bases which do not have disjunctions, the two approaches are identical essentially. So, in the next class we will try to extend this to formulas with quantifiers, and then we will move on to another approach to default reasoning, which is more discriminative in its approach essentially. It is not like everything or nothing kind of a thing. Here it is everything or nothing essentially. Either everything is false, which is the closed wall assumption, or nothing is false in this example essentially. So, we will try and look at that sort of a thing in the next class.